Again. All right, so like we did last time, we started talking about domain and range here. So of course, we're trying to identify the domain and range. And just as a quick recap, when we are talking about domain, remember we are talking about the set of possible input values to a function, right? So what would that be for your independent variable, or the input variable as they call it. And then the range, of course, will be the set of the possible output values. So of course, uh, the y values, what would those come out to be? And we looked at how to identify domain and range based on some real world examples that we saw. And then, of course, we talked about the notation for writing domain and range. And most of the time, even though we can use inequality or the set builder notation, most of the time we do actually write it using the interval notation, right? So you can see that's the column on the right-hand side, the interval notation. And then, of course, going up on that, we looked at how to look at number lines, and then we were working with graphs. So this was the last example that we had seen. So basically, we are saying, if you look at this little statement over here, that, X and Y are not always going to be the input and output variables we use. Sometimes we will use descriptive variables, if they identify the problem that we are looking at and identify those variables better for us. So here's another graph we are looking at with its domain and range. Can we see those numbers? Let me make this a little bit bigger. Okay, so making the page bigger doesn't really affect the graph a whole lot, so sorry about that. But you can see we are talking about world population increase here. Again, your horizontal axis, you will see that's where we have the year. And then the vertical axis, we have the population increase, right? And that's based in millions of people, obviously. And you can see the source of the information is coming from the US Census Bureau based on their international database. So you can see that trend, right? Like there was an increase we are seeing somewhere in the early 1950s. We see that drop happening around the 60s. And since then, we've been pretty much growing as a population. So if you had to identify the domain, which remember is the input values, what do you think the domain for this example would be, this function would be? So will domain represent the year or the population increase? The year. The year, very good. And where would we say approximately, where do you think we are at with these? Looks like it, doesn't it? So if that's 50 at the starting point, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 1952 seems like a good starting point. And then how far do we go? Where are we ending at? 2002. Yeah, it kind of looks like that, doesn't it? Now, would we use parentheses or brackets when we're writing this in interval notation? Brackets, yes, because you do have to include your endpoints, your years from 1952 to 2002. And then what could we say about the range of the population? So that would be looking at this on the vertical axis. So maybe somewhere over there. Somewhere over there, maybe. Yeah, because we have what, 1, 2, 3, 4 marks between them, right? So intervals of 2, so 44. And of course, remember, this is in millions, so we're just writing the numbers without the millions. And then where are we ending the population increase at? Kind of, doesn't it? Yeah, I know my line is a little off. And then again, do we include the endpoints here, guys? Yeah. Excuse me. So brackets all around. So again, that is looking at a graph and trying to identify what your, how are they going to, oh, I did that wrong. I'm so sorry. I can't even believe I did that because I just went till the end, but we should be going to the highest point, not the end. My apologies. So yeah, so that will actually change that. So they're saying 88. I have mine at 86, but again, it's probably just the way I placed that line. But yeah, I mean, you still get the idea of how you are supposed to read the graphs and come up with your domain and range. So you can see our years were good, 1952 to 2002. And then for the population in millions, your textbook has 40, I'm sorry, to 88. So yeah, definitely a little bit off of where I placed the lines. And I just also realized what other error I made. And that was, again, not looking at the end of the line, but the lowest value, right? So that would be where 40 would be at. And then, of course, the highest one looks like it's this point. So yeah, if you kind of try to get it straight, it does look like it should be at 88. So 40 to 88. So yeah, sorry about that. But questions on this, guys? Okay. Okay, so some of our basic functions that we had looked at in the last sections, you can see we're again talking about the toolkit function. So we're basically saying that if you have a function f of x equal to c, then your domain is not going to be restricted because x can be anything. And again, if we look at these, on a graph, let's go back to our Desmos graphing. And let's say if we have f of x is equal to, I don't know, 4. So you can see what that graph will end up looking like. And we can kind of zoom out of that a little bit, but you will see it's basically going to be a straight line which goes horizontally, right? But that tells us that the x values can be anything because it's going to be parallel to the x-axis, which means your x will be all real numbers. And so you can see your domain for this guy is all real numbers. And in interval notation, of course, we write it out as -infinity to +infinity. But when it comes to the y value, of course, you will see for the y value, it just stays at that one number, right? And again, we can kind of zoom back in just to show you where we were at. And you can see we were at +4. Now, if I change that function, and let's make it -2, basically you'll see the same thing, right? It just moves down to -2, but the x values will still be all real numbers and your y value will be whatever this c is, right? So the range will be that one single number. So if it's a positive number, it's positive, negative number, negative. You can also be right on the x-axis, so at 0, but you can kind of see how your output in this constant function will come out to be. Remember your identity function, the reason why it's called identity is because your x and y values are going to be exactly the same. So if I change this to f of x equals x, which is another way of writing this would be y equals x. And that's why it's called an identity function because your x and y share the same values. And you can see what this function ends up looking like. So in this case, you will again notice that our domain will be all real numbers, but this time the range is also all real numbers for the identity function. And that's because of, again, we can zoom out so you get a bigger picture. But look at all those X and Y values when we zoomed out, that line still keeps going, right, in both directions. So yeah, for both your X and Y values, your domain and range for the identity function are going to be all real numbers. Then we talk about the quadratic function or the second degree function, which of course is our f of x equals x squared. So let's take a look at that. And this is going to be a parabola. And of course, I need to kind of get back to our home screen. So in a parabola, you will see obviously there are no y values which are negative, right? The graph is starting at 0 on the y-axis and it's moving upwards. And again, if we zoom out, you will see that parabola shape is still there, right? You're not seeing anything on the negative side of the y-axis. And obviously, as you zoom out, you will see that shape starts kind of losing its shape, right? The graph ends up looking like it's a straight line, but we know that's not true. That's just because of the zooming in and out, which is kind of what I had talked about last time, is we don't just depend on graphs themselves. We try to look at them more in an algebraic sense, but just putting it back in its original form. So here you will notice for the x values, there are no restrictions. And again, I can zoom out a little bit. So even though it looks like the graph's arms are going upwards, but if we were to follow the trajectory of this, what happens here basically is this arm of your graph, as the x values get really large, will, of course, cover all the x values as it's going up. And the same thing's going to happen on the left-hand side as the x values get really, really small. Your arms are going up, but it's also going to the left. So when you talk about the domain or the values for the input, you are actually going to have all real numbers for the domain of a quadratic function or a second degree function. So it's still all real numbers. But when it comes to the y values, as I mentioned, there is no graph on the negative side of the y-axis. So your graph starts at 0 and it's headed on the positive side of the y-axis. So when you look at the range for the quadratic function, you will see it actually starts at 0 and goes up to positive infinity. And of course, notice the bracket on 0 because 0 will be included as part of your y value. So just imagine if we take this function f of x equals x squared, and I replace that x with 0, right? So of course you would be doing 0 squared, which is 0 times 0, and that comes out to be 0, right? So that's why you are including 0 in your range, because you can see that our y value will be 0. But because of that square on the quadratic function, even if you put a negative x value in, you're not going to get a negative y value, because keeping it simple, if I use my x value as -1, that will be -1 squared, which means we are multiplying -1 with -1, which becomes positive, right? So this is the reason why for the quadratic function, you are not going to have any negative y value. So your range will start from 0 and go to infinity. Does that make sense? Yeah? Did anybody on Zoom have questions? Okay. Our next one, as you can see, is the cubic function. So that's to the third power. So let's see what happens with a cubic. So let's change that exponent to a 3. And you can see the shape, of course, of the graph changes a little bit. But again, I'm going to zoom out here to show you. It does keep that S sort of curved shape, but obviously as we zoom out, it starts looking more like a straight line, but we know that's not the case. But what you should notice here is obviously we're using all the y values here, right? We've got graph on the negative side of the y value, on the positive side of the y-axis. So we are using all real numbers when it comes to the range, but you are actually also using all real numbers for your domain also. So even though the graph tends to be going, more in the vertical format, but it's the same thing we saw with the parabola. As your x values get large, you are still heading upwards, and you're heading upwards at a much faster rate, right? Because it's x to the third value, but you are still going to use up all the values on the x-axis. And same thing on the left-hand side. As your x values get really small, you will start going downwards on your graph. So for a cubed function, you are actually looking at domain and range of all real numbers. So again, for the cubed function, it's negative to positive infinity for both domain and range. So that's your third degree cubic function. Now let's look at the reciprocal function. And this one is 1 over x. Let's come back here, get rid of that guy. So 1 divided by x, and you will see how this ends up looking like. You should also recognize that since the x is in the denominator, we also call these as rational functions because it's got a fraction, right? So whenever your x is in the denominator, that actually means there's going to be some number which is going to make your x into a 0, which means you cannot use that number in your domain. So if you look at this function here, we've got 1 over x, and basically the idea is if your x is equal to 0, right? This will become 1 over 0, and we know that is undefined. So since we know division by 0 is undefined, we put that restriction and we say that x cannot be equal to 0. And you can even see in the graph, there is no graph at the x value of 0, right? You will see this arm of your function is getting really close to the y-axis, but it's actually never going to touch the y-axis. Same thing's happening on the left-hand side. This arm is getting really close to the negative side of the y-axis, but again, it's not going to touch the y-axis. And that is because what you see, why this is happening is, of course, because we know at 0 the function is undefined, but also you have a vertical asymptote at x equals 0, which is sort of this imaginary line that is right on top of the y-axis where our x value is equal to 0. So this is what we call as a vertical asymptote. And we will actually talk more in detail about this when we are talking about rational functions. This is just sort of an intro. You will notice the same kind of behavior happening near the x-axis also. So you will notice that this arm of our graph is getting really close to the positive x-axis, but same thing, it's not going to touch it. And same behavior on the left-hand side. This is, again, same thing like a vertical asymptote. This guy is going to be a horizontal asymptote, which is going to be at the line y equals 0. So you actually also have a horizontal asymptote in this reciprocal function. So vertical asymptote is the vertical line, x equals 0. Horizontal asymptote is the horizontal line, y equals 0. So this actually tells us you cannot include 0 in your domain, but you also cannot include 0 in your range. So for the domain for this function, we will be going from, okay, everything from negative infinity to 0 is okay. We cannot include 0. You know what, let me clear some of this writing because I want to show you that. So when we are saying everything from negative infinity to 0 is okay, we're talking about these values here, right? But obviously at 0, we have to stop. Then you can pick up on the other side of 0 and you can go to positive infinity. So then you can say, okay, from the other side of 0 to positive infinity is fine. We just cannot include 0. So in interval notation, you end up writing it with your union symbol in 2 separate formats. And that will be the same thing for the range, because also on the range side of things, we can say, as long as you are not including 0, you're fine. So from 0 to positive infinity, and negative infinity to 0 is fine. So negative infinity to 0, union 0 to infinity. As long as you are not including 0 in both your domain and range, you are good to go. And you can see that. Come on here. Okay, so you can see that right over here with the reciprocal function, your domain and range. So we cannot divide by 0, so you have to exclude 0 from the domain, and 1 divided by any value can never be equal to 0, so we know the range will not include 0, because if you divide 1 by any number, you're going to get an answer, right? You're not going to come up with 0 as the answer. So that's why we know for the range also you're not including 0. For the squared function for the reciprocal, so you are just taking that x on the denominator and making it a square. You will see that your graph for the function changes in this case. So obviously, because of that square on the denominator, you're seeing there are no negative y values, right? All the y values are going to be positive, kind of the same thing we saw in the quadratic function. But since this is still a reciprocal function, we still cannot divide by 0 because you have that x square in the denominator, which is telling you your x cannot be equal to 0. And again, on the graphs, we can see, right? We still have that vertical asymptote here on the y equal, sorry, not y, x equals 0, we still have a vertical asymptote at x equals 0 because that is not part of our domain. So you can see that same sort of behavior with the reciprocal squared function. So you can see the domain for the reciprocal squared function is similar to the reciprocal, where it goes from negative infinity to 0, union 0 to infinity, not including 0. But the range, you will notice, is going from 0 to infinity. And again, remember, guys, you have no negative y values here. There is no graph here. So you are starting at 0 and going up to positive infinity. But even though it's a little difficult to see, you actually do have a horizontal asymptote here at y equals 0. So you are not going to be including 0 in your range either. And honestly, just zoom in a little and you will see that there is actually a gap between your graph and the y-axis. It's just when it's in that original form, it looks like they are touching, but they're not. If you zoom in and get closer to it, you will notice that we do actually have a horizontal asymptote. So that's why we're not including 0 in the range of our function also. Any questions up until this point? No? You guys on Zoom? Okay, alrighty. So let's get into some of the cube and cube root and square root functions here. So you can see we're starting out with the cube root, and you will notice that it is actually telling us that you can use all real numbers for your domain and range. So let's take a look at what the graph looks like. So cube root, I think we have to go under functions for that. Okay, so there we go, cube root of x, and look at that shape. It literally, as you know, is the inverse function for the cube. So if you remember your cube function was vertically oriented, right? And the red is the cube root function. So it kind of takes a reflection across that y equals x line, the identity function, and it lays down in a way. But you will still notice that we are using all values on the x-axis and we are using all values on the y-axis. So as your graph goes to the right and the x values get really large, it's also heading upwards. So it will use all the y values as it goes upwards. On the left-hand side graph, as your x values are getting really small and they're becoming negative, your y values are also getting really small and going down further to the negative y value. So yeah, your domain and range for a cube root function are going to be are real numbers, so negative infinity to positive infinity. Square root function, on the other hand, and normally we write it just like this without that number 2 on the index. For the square root function, it is actually going to be different because for square roots, there you are, square root of x, you will see our graph is only on one side of the x-axis. So as you will notice here, our graph starts at 0 and it's going towards positive infinity. So for the domain, 0 to positive infinity, but you are actually including 0. For the y value, you will also notice there is no graph on the negative side. So even for the range, you are starting at 0, and then of course you're headed upwards towards positive infinity. So for the square root function, your domain and range are 0 to infinity. And this time, like I said, you are including 0 in your function. So you can see here, domain and range. So they are saying when dealing with a set of real numbers, we cannot take the square root of a negative number, so the domain is limited to 0 or greater. And this is something you should remember from your previous algebra class, but I can again do just a quick demonstration here. So let's say we want to take the square root of -4, and you will see it's going to tell us it's undefined. But if I took square root of +4, it would give me the answer 2. If I put the negative outside and did a square root of 4, you can see the negative just follows along, right? When it's on the outside. But when the negative is on the inside of your square root, it is undefined. So that's why we cannot have anything less than 0 in our square root. Now you can take square root of 0. So if I took square root of 0, of course I get 0, right? So 0 is okay, but anything less than 0 is not okay, which is where also that restriction comes in. So if you are not using 0 in the square root, you're actually not going to get an output of 0, of a negative number either. So you can see your range also then ends up starting at 0. So that's your square root function. And then your absolute value function is going to be, so you can just use ABS for the absolute value, and you can see the shape of this. So obviously you should again notice there are no negative y values here. You are using all the positive and all the negative x values here. So your domain for the absolute value function, as you can see, is all real numbers. But when you look at the range, the output values, you will see we start at 0, and then of course both the arms of your absolute value are going upwards, right? So that tells you that you will have positive y values, but not negative. And if you remember, one of the first days of class when we started lecturing, we had talked about how we think about absolute value being the distance, right, from a starting point. So since we talk about distances in positive numbers, that's kind of what we're seeing here also, right? All your y values are positive because, again, we technically would not think of a distance as a negative. So you can have 0 in your range, and obviously going all the way up to positive infinity. So this, like I said, since we are talking about absolute value as a distance from 0, your output obviously has to be greater than or equal to 0. So these were our toolkit functions. Now, what if we build up on them? So let's take a look at these guys here. And actually, I don't want to show you the solution just yet. So let me open up our blank Word document here. Okay, there we go. So let's take a look at, when we modify some of these functions, how we would come up with their domain and range. So let's start with that first one. We've got f of x is equal to 2 times square root of x plus 4. So now you cannot just use the same domain that we had in the square root function because that just had an x on the inside, right? This guy has an x plus 4. So whenever you are working with, and this will be true for any even numbered radical, so square root, fourth root, sixth root, same thing. If it's an odd numbered radical, like a cube root, fifth root, seventh root, they will be different. So in this example, you actually start with what is inside the square root. So you've got x plus 4. You set it equal to or greater than 0. So you actually set it up as an inequality. And you solve for x, which means get x by itself and move everything else to the other side. So we go ahead and subtract 4 and move it to the other side. And you will see we end up getting x is greater than equal to -4. So that actually gives you your domain. That right there is telling you what your domain can be. So if you think about this, on the x-axis, we are saying you can go from -4, here's 0, and then these will be all the positive x values here. So, basically think about this as going towards positive infinity here, negative infinity here. So we are saying x can be -4 or anything greater than -4. So in your domain, you will write it out as brackets, -4 to infinity. Now take a minute and think about how this will affect our range. What will the range for our function end up looking like? Now, I know they're only asking us to find the domain, but I want us to think a little bit in terms of what the range would look like. So what do you think will happen if we put the smallest x value into the function? What will it give us? Okay, so if we take our function here, and we plug in our lowest value of -4. So you are doing 2 times x is -4 plus 4 on the inside, right? So -4 plus 4, of course, come out to be 0. And of course, we know square root of 0 is going to be 0, right? So we end up multiplying 2 times 0, which will give you 0, right? So that actually tells you that when I use the lowest x value that we know from the domain and plug that into our function, it looks like you are actually going to be starting out at 0, and we should be, ooh, how did that happen? And we should be heading to positive infinity. And obviously we can do a quick check with our graphing calculator. So let's do that. Where are you? There you are. So let's plug this in. So we've got f of x is equal to 2 times square root of x plus 4 on the inside. So look at that, right? We are starting at -4 on the x-axis and we are headed to the right. So that's your domain of going from -4 to positive infinity on the x. And then for the y-axis, your lowest value is 0 for the y. And then, of course, our graph will be heading upward. So you can see you are looking at 0 to positive infinity when it comes to the range. Now, in your textbook, they're only showing you the domain values here, so they will not show you how to calculate the range, but hopefully this helps out. Questions on this one here, guys? Ladies? On Zoom? No? All right, let's look at the second one then. So for part B, we are given g of x is equal to 3 divided by 6 minus 3x. So again, if the x was not in the denominator, you would have no restriction. So if that x had been on the top instead of the bottom, your domain would have been all real numbers. But because the x is in the denominator, that tells us there's a possibility of the denominator equaling 0. So that's the number we have to not include in the domain. So all we need to do in this example, guys, is take that denominator and set it equal to 0 and then solve for x, right? Just like you would be solving any equation. So we can start by, I guess I want to make the x positive, so I'm going to go ahead and add the 3x and move it to the other side. We are left with 6 on the left, 3x on the right. Divide both sides by 3. Get x by itself. And of course, 3 goes into 6 2 times, right? So you can see in this case, when we took the denominator and set it equal to 0 and solved it, you are come with x equals 2. What this tells us is if your x is equal to 2, your denominator will become 0. So let's do a quick check. I'm going to take our function and replace the x with 2 and see what happens. So you've got 3 divided by 6 minus 3. Again, our x is 2. So that will be 3 divided by 6 minus 3 times 2 is 6. And you see that, right? You end up with 3 over 0, which again, we know is going to be undefined. So this tells us x cannot be 2. So every other number is okay except for 2. So your domain, and again, guys, if it helps to visualize, go ahead and draw a number line. So we know negative infinity is on the left, positive infinity is on the right. 0 is going to be in the center, and then our 2 is, somewhere over here. So we are basically saying do not include 2, but everything else is okay. So that means from negative infinity right till you get to 2, just not including it is okay. So that would be the interval from negative infinity to 2 with parentheses. On the other side of 2 to positive infinity is okay. So that means you're going from, again, not including 2 to positive infinity, right? And then you use the union symbol to join the two intervals together. This will be your domain. Any ideas on what our range could be here? Do you think it could be all real numbers for y, or will there be something that the y also skips, kind of like how we saw in the reciprocal function 1 over x? Okay, let's check that. But before we go into that, you can see the solution from your textbook. So negative infinity to 2, union to infinity as far as the domain for that second function goes. But yeah, let's check its graph, because I don't think your y value is going to be all real numbers. All right, so you have 3 divided by, and I'm actually going to put this in parentheses because Desmos can get finicky sometimes. 6 minus 3x, yeah, all right. So you can kind of see what your graph looks like. So you should notice, and we can use vertical lines to help us out. So we know we cannot include x equals 2. And you can see that's that red line, which is now actually acting as your vertical asymptote in this case. So your graph will get closer to that x equals 2 line, but not touch it, not cross it. But we are also noticing 0, right? On the y-axis is a horizontal asymptote, because you can see this part of your line, come on, gets closer to the x-axis, but it's not going to touch. And you can kind of, move your graph a little and you will see it's getting closer and closer, but there's always going to be that gap between the x-axis and your graph over here. So yeah, it's actually telling you you cannot have 0 as your y value. So your range for this guy will be, you can see we are going down to negative infinity here. So you're going down to negative infinity, but you'll stop at 0. And then you'll pick up from 0 again and go up to positive infinity. And then you are using the union symbol to again combine the two intervals. And then, you can obviously play around with some x values to see what answers you come up with, but you will never get 0 as an output for this function. Questions? No? Okay. So we're building up on this now, guys, and we are getting into piecewise functions. And basically the name kind of tells it by itself. We are basically saying your function is going to be in pieces, which means over different parts of the domain, you may actually have a different equation that defines what the function looks like. And one of our basic piecewise functions is actually your absolute value function. So yeah, we do define it as a single function. F of x is equal to, within the absolute value symbol, f of x is equal to absolute value of x. We saw the domain and range for this function. So we know the domain is all real numbers and the range is greater than or equal to 0, which means it goes from 0 to infinity, including 0. So how do we define an absolute value number as a piecewise function? And they kind of go into the absolute value can be defined as the magnitude or the modulus of a number. The real number, basically where you look at it without its sign. So again, that idea of a distance from 0. So the idea is if your original x value is positive, the number stays the same, right? You get the same value as x. However, if the original x value was negative, it changes to positive, right? So how does that change happen? And this is kind of what they are defining it as. So if your x is a positive number or 0, so let's say if x was 0, you get 0. If x was a positive number, the absolute value would keep it positive. But what happens when the number itself is negative? So let's say if I had f of -1, by this definition, we are saying put an extra negative sign there, and then your x also happens to be negative, right? So two negatives become a positive, and you can see how a negative number changes into positive. And of course, we can use that for any negative number. So you already have the negative from the equation, and then x itself is bringing a negative sign, and the two negatives become positive. So a piecewise function for an absolute value can actually be defined using these two definitions. Let me see, do they show that here? No. So if I had to rewrite this absolute value function, I would write it as x if x is greater than equal to 0, and negative x if x is less than 0. So this is how you define the absolute value function as a piecewise function. So you will see this is what I mean. So we are saying if your x values are 0 or greater than 0, use the top definition. If your x value is negative, use the bottom definition. And the result is still going to be the same. We're always going to get positive answers or 0 when you're using 0. So they are saying since this requires two different processes or pieces, the absolute value function is often called the most basic piecewise function. So here's your definition. A piecewise function is a function in which the formula used depends on the domain, upon the domain the input lies in. So basically you will take how many ever pieces it has, 2 pieces, 3 pieces. You take that formula and then you define on which part of the domain does that formula apply. So let's take a look at this example here. number 126. So they are saying a museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for 10 or more people in the group. So set up a function relating the number of people n to the cost of c. So we're basically saying it's going to be $5 per person as long as you have between 1 and 9 people. So that's going to be 5 times n, right? Number of people is the n. And then this is going to be between 0 and 10. And you will see we're not including 0 and 10, right? Because we want it to be between 1 and 9. Now, some might say, could we have written this as 1 less than equal to less than equal to 9? Yes, you could have, because then that says minimum of 1 person, maximum of 9 person, but they're kind of going with that more open interval, 0 to 10, not including the endpoints. The other part of the problem said, well, you can have a fixed $50 fee for 10 or more people in the group. So you can see we are saying if there are 10 or more people, because you're doing less than equal to, right? And that's going to be a fixed fee of $50. So that's how we would define this as a piecewise function. And then, of course, since we are using cost as the function definition, you can see we are saying cost is based on the number of people. So that's where the C of n is coming into play. Oops, sorry. Okay, then let's look at our next example here. They are talking about a cell phone company uses the function below to determine the cost C in dollars for G, which is the gigabytes of data transfer. So you can see over here, they're telling us C of G is equal to 25 if G is between 0 and 2, not including the endpoints, or C of G is equal to 25 plus 10 times G minus 2 if the G is greater than or equal to 2. And they're asking us to find the cost of 1.5 gigabytes of data values and the cost of using 4 gigabytes of data. So let's take a look at this guy here. So basically, they're giving you the piecewise functions. Obviously, we need to know how to read it, right? How do we understand what's being told to us? So remember, C is the cost, G is the data transfer usage, right? So in gigabytes. So they are telling you the cost will be $25 if we are using 0 between 0 and 2 gigabytes, right? So if you used 0.1 gigabytes to, let's say, 1.9999999, you will be paying a fixed cost of $25. However, if you are using more than 2 gigabytes, right? If you are using more than 2 gigabytes, then your cost will be based on this. So you can see they are actually going to be charging us that fixed fee of $25. Plus, we will have to do G minus 2. So that's, removing that initial whatever we did for that, because you're already paying $25 for that first 2 gigabytes of usage, right? Anything less than 2 gigabytes. So since you're already paying $25 for that fixed fees, you are taking 2 gigabytes out of your total usage. You're doing G minus 2, and then it's going to be $10 per gigabyte use. So that's how they are breaking this down. So you're doing your $25 fixed fee plus $10 into G minus 2. So if they are giving us a cost of 1.5 gigabytes, well, 1.5 falls in this range, right? Between 0 and 2. So that means your cost for 1.5 gigabytes is going to be $25 even, right? No math needs to be done. However, if you are using 4 gigabytes, so the next part of the question was 4 gigabytes. So if you're doing 4 gigabytes, then obviously that means we're going to the second part of our formula here. So for 4, you will then be using 25 plus 10 times you have to do g minus 2. Our g is 4. So remember, the first 2 gigabytes you use, you're already paying that $25. So that's why we are subtracting 2 from 4. And of course, 4 minus 2 is 2, which means you are paying $10 for those additional 2 gigabytes you used, which will of course be 20 and 25, which means we end up paying a total of $45 for 4 gigabytes of data transfer. And of course, you guys can see the math from the textbook here. So making sense of also what the piecewise function is telling us is also important. And then the other part is knowing when to use which piece, right? So like I said, 1.5 falls within the range of 0 to 2. That's why we use the first part of the piecewise function. 4 gigabytes is greater than 2, so that's why we use the second piece of the function. So you do have to be careful about looking at the domain and then deciding what you need to use. Question on this example here, guys? Okay. Let me know if something does come up. Alrighty, our next example here is asking us to sketch the graph of the function. So you can see we are doing x squared if x is less than equal to 1, 3 if x is between 1 and 2, not including 1, but including 2. And then f of x is 6 minus x if x is greater than 2. So you can kind of see how they are doing this separately, just to kind of show you each component. So the first part of the graph function is telling us you are using x squared if x is 1 or less than 1, right? So you can see we have a closed circle here at 1, and then you can see what the graph ends up looking like here. The second piece tells us the value is going to be 3 if your x is between 1 and 2, but not including 1. So you will see how we have an open circle here, a closed circle here to represent what's included, what's not included. The last piece told us x minus 6 for all values greater than 2. So you can see x minus 6 for all values greater than 2, what it looks like. But remember, this is all one function, which means we're supposed to put it all together like this. So I actually want to walk you through how we would do this. So if you were drawing this graph, how would we go about doing that? So creating a table is always a good idea when you're dealing with something like this. So for each of the function, we'll create a table. So the first one was x squared, the second one was 3, and the third one was x minus 6. So remember, the first function goes from anywhere for x is less than or equal to 1. So I can start with 1 and then go for numbers smaller than 1, right? So you can see for x squared, you're of course doing 1 times 1, which is 1. 0 times 0 is 0. Negative 1 times negative 1 is positive 1. Negative 2 times negative 2 is positive 4. Negative 3 times negative 3 is positive 9. So you get your points that you need. Then the next one said if you are between 1 and 2, including 2, you use 3. So technically, guys, they are telling us that 1 is not included in that second domain for the second piece. But we do want to know, are the two graphs going to be touching each other, or are they going to be separate? So even though we are not including 1, I am actually still going to use 1 in my table because I want to know where the point is going to end up at. So when I use 1, obviously we're still at 3 because you just have y equals 3 for your x value. When we use 2, you are still going to be at y equals 3 because this is a constant function. So one thing you should notice is we did not get the same value for 1 when we did the first piece and the second piece. So that tells you they will not be touching each other. They are going to be disconnected, which is what we wanted to know. Now the third one, x minus 6, is also saying for x greater than 2, but same logic. I want to know, are the two pieces touching or not? So even though we are not including 2, I am still going to use 2 in my table because I want to know what it looks like. So when we solve this, you are doing 6 minus 2, which will of course give us 4, and then we can do a couple more numbers after that. 6 minus 3 is going to be 3. 6 minus 4 is 2. 6 minus 5 is 1. All right, so we've got our points now. Now what will the graph end up looking like? And this is, again, just a very rough sketch here, guys, just to show you what this guy would end up looking like. So let me actually move our tables. All right, so let's take a look at what the graph would look like. So our x-axis, our y-axis, let's see, we're doing -1, 2, 3, 4, 5. Probably not going to be able to do that +9 for the y value, but we can try. All right, so let's see, we started at, and remember here you are including the 1. So we started at 1, which was at +1. So remember, this is where you had the closed circle at 0, 0. -1 was at 1, -2 was at 4, 5, 6, 7, 8, 9. Okay, I guess I can kind of get that. So here's our partial parabola, right? Then, even though we were not including 1, we wanted to know where it started in the second piece. So you went from 1 to 3, but this is where we will do an open circle. And then at 2, you were including the 3, so closed circle. This is what it looks like, just a little horizontal section of a line. And then even though in the third piece you were not including 2, we did want to know where it starts at. And you can see we got the ordered pair 2, 4, which means you will have an open circle here at 2, 4. Then we had 3, 3, 4, 2, 5, 1, and then of course you would have 6, 0, and then 7, -1 if you kept going, because this is going to be a straight line, which is going downwards. So this is how you would do if you were doing, by hand, if you were trying to graph different pieces. And obviously you will see that's exactly how your textbook has it. So you can see each of the individual pieces. So this was your parabola on the left, the constant function on the right, and then the 6 minus x over here. You can see where all the open and closed circles were based on the definition of your piecewise function, and then putting it all together. You can see. So unfortunately, in this example, the 3 pieces do not connect, but you can see putting those open and closed circles is going to be very important, because if somebody was only looking at the graph, they should know where the numbers were included and where they were not including. So open and closed circles is going to be very important. And sometimes the graphs touch, sometimes the different pieces will still touch each other, and obviously sometimes they don't. So this is how, just to kind of show you, if you were working this by hand, how you would go about doing your piecewise functions. All right, let's take a look at this one. And again, I'll hide the solution for now. Let's move this guy up a little. Okay, so we have at Pierce College during the 2009-2010 school year, tuition rates for in-state residents were $89.50 per credit for the first 10 credits, $33 per credit for credits 11 through 18, and for over 18 credits, the rate is $73 per credit. And you can see the source where they got that information for. So they're asking us to write a piecewise defined function for the total tuition capital T at Pierce College during that 2009, 2010, and it's going to be a function, of course, of the number of credit hours taken. And they're saying be sure to consider a reasonable domain and range. Okay, so we know we are talking about the tuition based on credits, right? So your capital T and little c for that. It does look like they broke it down into three categories. So you have $89.50 if our credits were the first 10 credits. So how do you think we can write the first 10 credits here, guys? How would you write it as a domain for that part? Would we do it like we saw in that one example? Okay, yeah, that's what I was wondering. So you can write it that, or did you want to write it like between 0 and 10, right? We saw in one of the examples. So either one of those formats would be fine. So the first 10 credits, are you including 10 in that?
Yes.
Yes, you are. So you can write it like this, guys, or if you wanted to write it as 0 between, C between 0 and 10, you can, that should not be a 0. So either of those, domain formats. What happened? Why are you not showing my writing? There we go. Everybody okay with that? Yeah, okay. What would we do for the second part, which was for the first 10 credits, $33 per credit for credits 11 to 18. So 33, of course, is the tuition, right? Do they want us to write for the total tuition? Okay. How are you defining the domain here? For 11 through 18? So would we say C is between 11 to 18 and include the endpoints? Or would we say starting at 10 and then going all the way through 18? Starting at 10? So this would be a three-piece inequality. Oh, come on, buddy. So 10 to 18, right? Because we cannot include 10 since you are already including 10 on that first interval. And it does tell us what the first 10 credits, right? So it technically starts from 11 to 18. Now, usually we don't have, at least I am not familiar with half credit classes. But if, let's say, you did have a half credit class, writing it as 10, not including 10, because anything more than 10 is what we're saying, right? But since the example specifically says 11 to 18, if you wanted to, you could write it in that format also, because they are specifically telling you from 11 credit hours to 18. And then I think that brings us to our last one, which said for over 18 credits, the rate is $73. And then how would you write the domain here? For over 18. Would we just say greater than 18? Because again, you can't include 18, right? Because 18 is included here. Now there's one piece missing from the function definitions because I just put the dollar amounts down. What do I need to add to our functions? There's something missing in each one of these. pieces. What should we have?
For the 33, do you want to add it with the 8950?
For the 33, do I want to add it with the 8950? Okay. And what else? There's still something else missing. Where's our variable?
You need C minus 10.
Well, we need C, right? For the first one, you just need C because the 8950 is for each credit hour, right? So you need to multiply 8950 by how many credits you are taking. So the first one, you need to have a C on it. Right? Because how do we know what you're multiplying? It's obviously not going to be just 8950 for all 10 credits. It's per credit, right? And I'm pretty sure they did tell us that. Yeah, 8950 per credit for the first 10 credits. So this is how you would write out the first part. Now, you were saying about part B. How would we rewrite part B? So I think I may actually need a little bit more space. Nope. We don't have to write this all out. So what do we need to do for part B? Because you're only starting at 11 credit hours, right? To 18, but we do have to take into consideration the first 10 credit hours, don't we? This is not working. Okay, I may have to make space here. All right, first part 8950 multiplied by C. So how much will it cost us for the first 10 credit hours?
8950 cents.
Per. So what's our total cost? Because remember, this is in tiers, it's tiered. So you are doing 8950 for the first 10 credit hours. So I don't know, it's kind of in the middle, but you can see it's going to cost us $895, right? Total for the first 10 credit hours. So when you are taking that into consideration for part 2 of this, you will be adding that $895 plus $33 for each credit hours, right? So how will we write the plus 33 part? Like what do we need to do to modify it?
Plus 33 to each credit over, would it be?
Like, are we just multiplying it with C? And I can go back to the textbook.
C.
Very good. Yeah, because if your total credit hours are 12, for the first 10, you are paying $895, right? So it was kind of like we did with the gigabytes example. So you will be doing 33 times C minus 10 to make adjustments for the first 10 credit hours. Alrighty, so think about that and tell me what part C or the third part of this example should be, where for over 18 credits, we are now paying $73 per credit. And remember, this is going up to 18, right? So what's the total cost of taking 18 credit hours? How do we calculate that? So for the first 10, we would be paying $895.
33 times 8.
Basically, yeah, because you're doing 18 minus 10, right? If you were putting it in the formula. So you are doing 18 minus 10, which will be 8. And you can see that means you will actually be paying a fixed price of $11.59 plus how many ever credit hours you take over 18. Oops, sorry, wrong one. Come on, I have too many windows open, sorry. Okay. So how do we rewrite the third piece? What was that, 1159?
Yeah.
Plus 73 for each, and then how do we write the variable part?
C minus 18.
C minus 18. Right? Questions here? People on Zoom? So you can see how just writing the price itself is not enough, right? The different tiers of 80, 89.50, $33. They went down to 33 and then went back up to 73? Huh. So it's actually more expensive to take more than 18 credit hours. If for 11 to 18, you can only do 33. So I wonder if that's a way for them to discourage students from taking too many credit hours, because that can be challenging, right? For at least some students. But yeah, so you can kind of see that we need to take each tier into consideration and then kind of work backwards from there, right? Subtracting the level that you already did before. So you should be able to see the breakdown from your textbook. So yeah, the first one was straightforward, $89.50 multiplied by your C. And oh, I did use my symbol incorrectly here, sorry. Less than equal to. So up to 10 credit hours. And then you can see they did actually go with 10 to 18, not including 10, but including 10. And then of course the math like we did. And for the last one, they just went with C greater than 18. So just a little bit of a different example than what we had seen with the other piecewise functions. But like I said, in some ways, this guy was similar to your gigabytes example, because we had to think about subtracting those gigabytes from the first piece of the problem. All right, guys, so these are your piecewise functions. And you can again see the exercise problems you have available here. Let's actually look at number 21 here, because I do want to do another piecewise example. So let's look at number 21. So you can see we are given f of x is equal to, and there are two pieces here, x squared minus 2 if your x values are less than 2, and 4 plus absolute value of x minus 5 if your x values are greater than equal to 2. So you can see the different pieces. Let's do a table for each of the piece. So anything less than 2. So honestly, again, I do want to know what the graphs will look like right at the value of 2. So I will use 2 for the first piece also. And then, of course, anything smaller than 2 is fine. So maybe just pick a few basic numbers. X squared minus 2, and we can do the math here on the side if you want. So if we are using 2, that will be 2 squared, which is, of course, 4. 4 minus 2 is 2. We are doing 1 for the x value, so that's 1 squared minus 2 is 1 minus 2, or negative 1. 0 squared minus 2, of course, will be 0 minus 2, which will give us negative 2. Now here, remember the x is bringing the negative sign, so that's going to be in parentheses. So you are doing negative 1 squared minus 2, which actually becomes positive 1 minus 2, which ultimately gives us negative 1 as our answer. Same thing, you do negative 2 squared first, which will become positive 4. 4 minus 2, of course, also gives us 2. And it should not be a surprise to us, because you do have x squared, which is a quadratic, which means we will be looking at least a partial parabola over here. Now, for the second piece, it is actually asking us to start at +2 because it goes from +2 or greater than 2. So we can do 2, 3, 4, maybe a 5. And let's see, this guy will give us 4 plus absolute value of 2 minus 5, which will be 4 plus 2 minus 5 is -3. Absolute value of -3 is +3, which will become 7. And of course, guys, you can plug this into a calculator if that makes it simpler for you to work with. 4 plus absolute value of 3 minus 5 will, of course, be 4 plus 3 minus 5 is -2. Absolute value is +2, so that's a 6. 4 plus 4 minus 5 inside the absolute is 4 plus 1, which is a 5. And then the last one, can you see that? Yeah, 4 plus 5 minus 5, of course, is absolute value of 0, which will give us a 4. So let's see what happens here. We may need more numbers, I'm not sure, but let's work with what we have and then we can see if we need to do more. I'm actually going to delete this because I need space to draw our graph. There we go. Alrighty. Okay, so a quick sketch here. We are starting at 1, 2, 3, 4, 5, 6, 7, 8, maybe. You can also graph these in Desmos. I will need to go and review how to restrict the domain. It's been just a little time since I've done that, so we can definitely look at that. But let's take a look here. So remember, you were not including 2 in that first piece of your function, but we wanted to know again, would the graphs be touching each other or not, the 2 pieces. So for that, we got 2 and 2. So remember, this is where you would have the open circle because 2 was not included in the domain of the first piece. Then we had at +1, we were at -1, at 0, we were at -2, at -1, we were at -1, at -2, we were at +2. So you can see that's that parabola I was talking about. So this is kind of what you would get from that first piece of the function. For the absolute value function, the second piece, we went from 2 to 7. So that's 2, 3, 4, 5, 6, 7. So over here, but this would be a closed circle because you are including 2 over here. And then we had 3 at 6, 4 at 5, 5 at 4. So it definitely looks like it's going down from here, which means we actually do need to go a little bit because we're not getting that full V shape of our absolute value here. So if we did 6, that would be 6 minus 5 is 1. So this would add up to a 5. So at 6, we are at 5. So is this where we are turning? This one? Seems to be, but let's check. Okay. So our first piece is x squared minus 2. Trying to remember if this is how we do it. Okay, that worked. All right, awesome. And then we are doing for the second piece was y equals 4 plus absolute value of x minus 5. And then this one was for x greater than equal to 2. All right, so let me actually, I'll keep the graph, but I'll delete the writing. So you can kind of see what our graph looked like and what Desmos is showing us. All right, that's what I was hoping to see. Yeah, so you can see you do get that absolute value shape. We just obviously had to get enough points on our table to make sure we knew how the V was going to change directions. And then, of course, you can see the parabola of the, stop doing that, first piece of the function. But again, these two were not connected to each other. So you can see you're going to be including it at the absolute value function, but not including it on the parabola. Unfortunately, on graphing calculators, you are not going to see those open circles. So what you will see is just shy of where that point should be. It's not going to go all the way to that corner, but it's really going to be hard to identify that, especially if you're looking at those smaller screens, you can't really tell the difference between open circle and closed circle. So that's why you will see in our textbooks when we do the graphs for these, we always use those open and close circles, and we should be able to see the, okay, looks like they didn't give us the graph, they just gave us the points here, but that's fine. All right, questions for piecewise functions here, guys? Okay. If you do not have any questions, that actually wraps up section 1.2 for us. And then you can see we are building into section 1.3 here. So here we're actually getting into rates of change, which you should actually remember that from when we talked about slope, because when we talk about rise over run, slope is actually a rate of change, and you can kind of see some of the table over here with the example. So they're saying since functions represent how an input quantity varies based on the input, how an output quantity varies on an input quantity, it is natural to ask about the rate at which the values of the function are changing. So here we're talking about C of t represents the average cost in dollars for a gallon of gasoline T years after 2000. So basically how the prices have changed since the year 2000. So you will actually notice that for T, you are looking at numbers like 2, 3, 4, 5, 6, 7, 8, 9. What does that actually tell us if we are doing this after the year 2000? Because it's not given us as 2001, 2002, 2003 in those numbers, right? They're just giving you 2, 3, 4, 5, 6, 7, 8, 9. So what does that tell us? Anybody on Zoom have an idea? What does the year 2 tell us, the t equals 2 in the table? What year are we looking at? Yeah, so what's happening in these cases is when they say after 2000, 2000 actually becomes your year 0. So anything after that, so like year 9 would be 9 years after 2000. Sometimes they may do like 1995. So 1995 then becomes your year 0, and then you are counting how many years after that would be like 9 years. So of course, in this case, it would be since 2000. So you can see in year 2002, the cost of gasoline was $1.47, but then by the time we came to year 2009, the cost was 214. But look at these ones here around 2006, 2007, you can see the gasoline prices, even from actually 2004 to 2005, the gas price went up, right, to $2.30, then 2.51 to 2.64. In 2008, it went up to $3.01, but then it dropped in 2009. Does anybody know what was happening in those years from 2005 to about 2008, 2009? So 2005 was when Katrina happened. And that really skyrocketed gas prices because, obviously being a coastal city, a port, a lot of the gasoline was not coming in. 2008, 2009 was when we hit recession. And this was, when the government had to bail out like a lot of these automobile companies, they bailed out a lot of these national banks and stuff. So there was like a massive recession that happens. And usually instead of prices going down, they go up, right? Especially for gasoline. So you can see there was definitely fluctuations. I came to the US in fall of 2000, and I remember seeing gasoline at $1.18, and my cousin, sister, and I were like, oh my God, that's so expensive. Because even at $1.18 in the year 2000, right? We're talking like what, almost 25, 26 years now. It was a big amount. And obviously now gas is just, you can't even imagine getting $1 something for gasoline. So yeah, you can see how those trends affect your gasoline prices. So yeah, you can see between the years 2002 to 2009, the price has increased from $1.47 to 2.14, and that's an increase of 67 cents. Now they are saying while this is interesting, it might be more useful to look at the price change every year. And you are noticing that the price change didn't change the same for each year. And obviously that's where we actually talk about the average rate of change, because year to year, the change is going to be different. But if we wanted to do a comprehensive rate of change, that is where we bring in this idea of doing an average rate of change for a specific amount of time. So if you go from 2002 to 2009, that's a difference of 7 years. And you can see the gas price changed by 67 cents. So on an average, we can say that the gas of price has increased by 9.6 cents each year. But remember, that means we are averaging out these larger numbers also that were in those years of 2006, 2007, even 2008, because you're taking an average of all the changes that have happened over that 7 year period. So your definition for rate of change describes how your output quantity changes based on your input quantity, and your units on a rate of change are going to be your output units divided by your input. So you can see in our gasoline example, we are doing dollars per year, right? Because whatever number or unit is on the top goes first, and then you're doing per whatever the value of your denominator is. We, of course, talk about rates of change in a lot of different areas. Population of rat increases by 40 rats per week. A barista earns $9 per hour, so dollars per hour, right, is your rate of change. A farmer plants 60,000 onions per acre, so that's your rate of change. Also based on onions per acre, a car can drive 27 miles per gallon. Population of gray whales decreases by 8 whales per year. The amount of money in your college account decreases by 4,000 per quarter. So all of these are rates of change. And then, of course, you can see the definition for an average rate of change between two input values is the total change of the function values. That's your output. So you can see basically you take your changes in the output and divide it by the changes in your input. And this formula should look familiar to you because that's your slope formula, and your slope calculates your average rate of change. So you can see we are doing y2 minus y1 divided by x2 minus x1. So slope is where we first start talking about an average rate of change. So you can kind of see the examples here. We are saying using the cost of gas function from earlier, find the average rate of change between 2007 and 2009. So that would be 2007, the gas price was 264. 2009, the gas price was 214. So you can see we take the difference between 214 and 264. Now you will notice we put the 214 first, and from that we subtracted the 264 because you take the newer value first and subtract the older value from it. So you are not going to set it up where you put the larger number first and the lower number second, because remember, too far. This is the newest value we had, and from that you are subtracting the old value. So if it comes with a negative, it's fine. You come up with a negative answer. So you can see, yeah, the difference between $2.14 and $2.64 is a difference of 50 cents, and that's going to be in a negative. Of course, from 2007 to 2009, we're looking at a difference of 2 years. So you can see your average rate of change is basically we went down on an average by 25 cents each year. So the negative number tells you you're going down, which means your rate of change is decreasing. If it's a positive number, it tells you your rate of change is increasing. So that's how you kind of keep track of the trend, right? Is it going up or is it going down? Your next example, using that same function for gasoline, you can see we are talking between 2003 and 2008. So 2003, we were at $1.69. 2008, you are at $3.01. So same thing, right? $3.01 is the newer one. From that, you'd subtract the older value of $1.69. That was a difference of 5 years. So you can see over 5 years, so basically from 2003 to 2008, the gas prices went up by 26 cents approximately, right? 0.264. But from 2007 to 2009, they actually went down by 25 cents each year. So you can see how between different years, your rate of change can be different within the same example. So in one function, it decreased, but in the other one, it increased. So again, as I said, that's kind of where your positive and negative values will come into play. All right, guys, we'll continue with this discussion next time. So for now, for tonight, you are working on 1.1 homework. And then we will keep 1.2 homework deadline for Friday, but let's see what we do for 1.3. We may need to move that due date, but we'll keep the 1.1 and 1.2 dates the same. Okay. All right. If anybody has a question, please feel free to stay back. And if not, then I will see you guys on Wednesday. So have a great day, guys. Let me know if you have any questions. Take care, everyone. Be careful.